So 5.2 is going to start getting us towards our next topic. This is actually technically review, but we have to use the summation notation in 5.3, so we're going to review it. So sigma notation and limits of finite sums. So sigma notation is this sigma. You guys probably recognize this from sororities and fraternities. This is sigma. He means add them up. Whoop, where's my pen? Or find the sum of whatever comes next. So this says find the sum of all the AKs, where K goes from 1 to N. So add up K1, K2, K3, all the way up to add A1, A2, A3, all the way to AN. And that's what we've written out here. This is what that notation means. So we call this guy the K the index. And notice the K is in both places here. That's the part that changes. 1 is the starting point for the index, and N is the ending point for the index. AK represents the formula for each term in the sum. So you can see here, we start with 1 and we go up to 5. So we're going to plug in 1, 2, 3, 4, and 5. And we're going to plug it into this formula here. This formula is just K. So literally, for the first term, we plug in 1. So the first term is just going to be 1. Plug in the next value. So the next value is 2. Plug in 2 for this formula. Well, that's just 2. So we're going to add 1 plus 2. Keep going. Plug in 3, plug in 4, and plug in 5. That's what this notation is telling you to do. Add up the numbers from 1 to 5 because it's not doing anything to the numbers. So if we add these together, that'd be 3, 6, 10, 15. And there's the sum. All right, this one has a special guy here. Let's see what happens when we do this. So if we plug in 1, negative 1 to the first power is still negative 1. So this is going to be a negative times K. So negative 1 times 1. So we're plugging in K equals 1 here. So negative 1 times 1 is just negative 1. If we plug in K equals 2, our second term, negative 1 squared would be positive 1. And then K would be 2. Plug in K equals 3, which is our last value we're plugging in this sum. Negative 1 to the third is still going to be a negative 1 times the 3 is just going to be 3. So that ends up giving us negative 2. That's your sum. So this notation here is creates what we call an alternating sum. Notice the signs alternate every step of the way. If this had been something else up here, we'd have to be careful because it could change how our signs alternate. All right, this is our formula. We're going to plug in 1, 2, and 3. Those are the values that our sum says. So if we plug in 1, we get 1 over 1 plus 1. If we plug in 2, we get 2 over 2 plus 1. Plug in 3, we get 3 over 3 plus 1. So that's 1 over 2 plus 2 over 3 plus 3 over 4. If we get a common denominator, that would be 12. So we have to multiply this one by 6 to make this a 12. So 6 multiply, here, let's write it out. So we're multiplying top and bottom by 6 to get the common denominator. This one we multiply by 4 to get our common denominator. And this one we multiply by 3. Just trying to make the bottoms all 12. All right, so 2 times 4 is 8. 3 times 3 is 9. And we end up with, what is that? 23 over 12. That's your sum. Oh, I did it again. Gotta quit grabbing that by accident. Control Z. Yay, it went back. Okay. All right, we have one more sum here. So K, notice it starts at 4 this time. K can start at any number. Traditionally, it starts at 0 or at 1. In Calculus 1, we focus on starting at 1 typically, but it could start anywhere. All right, so K starts at 4. So the first number we plug in is 4. So 4 squared over 4 minus 1 plus plug in the last number because it only goes from 4 to 5. 5 squared over 5 minus 1. So that's 16 over 3 plus 25 over 4. Get our common denominator of, that'd be 12. So multiply by 4 and multiply by 3 to get our common denominator. So 16 times 4 is 64. 25 times 3 is 75. And they are over the common denominator of 12. So that would be a 9 and a 13. So 139 over 12 that does not reduce, so that would be the sum. There you go. Now, you can also have a summation already written out the long way, and you have to write the summation notation. So, we want to use this with 3 different starting values for k. So, where do we want to begin? Let's do a summation where k starts at 1. And we're going to go 1, 2, 3. Here, I'm going to write the k value underneath. So 1, 2, 3, 4, 5. So we're going to sum from 1 to 5. The question is, what's the formula? Well, it can't just be k, because k would be 1, 2, 3, 4, 5, and that's not what we see here. Do you see a relationship between the k value and the number up above it? Well, if you look at the numbers 1, 3, 5, 7, 9, they are all odd numbers, and we didn't skip any odd numbers. So, how can we turn each of these into an odd number? If I multiply by 2, they will all be even numbers. To make them an odd number, you would need to add or subtract 1 from it. So let's try. If I do 2 times 1 is 2. To get down to 1, I would need to subtract 1. Let's try it to this one. If I plug in 2 here, 2 times 2 minus 1 would give me 3. If I plug in 3, 2 times 3 minus 1 would be 5. 2 times 4 minus 1, 7. 2 times 5 minus 1, 9. There you go. That's your summation. That's one possible way to write this. All right, I'm going to erase the numbers underneath because we're going to try a different starting value. So let's say k starts at 0. So 0, 1, 2, 3, and 4. So our summation this time, k starts at 0 and goes only to 4. Now, does the same formula work? If I do 2 times 0 minus 1, I'm going to get negative 1. That's not what I want. 2 times 1 minus 1, that would give me 1. That's not what I want. So how do I make these k values turn into these odd numbers? Well, let's stick with the same idea. Multiply by 2 and you get even numbers. So this would be 0, 2, 4, 6, and 8. But each of those is 1 too small. So if we do 2 times the k value, we need to make them slightly larger. So 2 times k plus 1 is how we make odd numbers as well. But these odd numbers are having to increase. So 2 times 0 is 0, plus 1 is 1. 2 times 1 is 2, plus 1 is 3. All right, we do one more set. If we were in class, I'd let y'all pick the k value, but we're not there, so I'm going to pick it. So let's start our sum at k equals 2, just because I have no imagination. So if we're going to do 2, 3, 4, 5, 6. So we're going to sum from 2 all the way to 6. Each one of these has the same number of terms. It's just starting at a different spot, so it's ending at a different spot. All right, so how do we do this? It's going to be the same trick. You're still going to do 2 times k. 2 times 2, though, our first number, 2 times 2, is going to be 4. How much do I need to add or subtract to make that a 1? Well, if I'm at 4 and I need 1, I got to subtract off 3. Now let's make sure it works for the rest. So let's use this formula, plug in 3 for k. 2 times 3, 6, minus 3. Yeah, we got our 3. 2 times 4 is 8, minus 3 is 5. 2 times 5 is 10, minus 3 is 7. There you go. That's another way to write the summation notation. All right. Got a couple more examples right there. All right, so this one involves a fraction. Anytime you have a summation written out and it involves fractions, typically you're going to want to consider the top and bottom separately. Now we're going to start with k equals 1. So again, I'm going to write my k value just next to my numbers so I know what I'm doing. So I'm summing from k equals 1 to 5. So that's my summation. And we're going to look at this as a fraction. The 1 is usually going to throw you off. So focus on the rest and then just go back and check and make sure you get the 1 for your first term. What relationship is there between 3, 9, 27, 81 and their k values? And then 2, 4, 8, and 16. Well, these are actually 3, 3 squared, 3 cubed, and 3 to the 4th, aren't they? So let's rewrite these fractions. So move my k values out of the way so I can rewrite my fractions. So this is really 3 to the 1st, 3 to the 2nd, 3 to the 3rd, 3 to the 4th. On the bottom we have 2 to the 1st, 2 to the 2nd, 2 to the 3rd, and 2 to the 4th. Let me bring my k values back over. Remember, our k values were 1, 2, 3, 4, 5. Do you see a relationship between our k values and our fractions? Well, these are really close to our k values. They're each of our k values minus 1. So what I'm going to hypothesize here is that we're going to have a 3 to a power and we're going to have 2 to a power. The power is going to be whatever k is minus 1. Another way to write this is to write all of it, the 3 over 2, to 1k minus 1. Because it has the same power, you could write the power just over the whole fraction. But we have to check and make sure our first term works. Because whoops, not to infinity. That's calculus 2. You guys can wait until you get there for that. To 5. If we plug in 1, 1 minus 1 would be 0. 3 halves to the 0 power, what would that give us? That would give us our 1. So yes, this does work. And that is these are the only ways to write this if we're going to start with k equals 1. All right? Now, algebra rules for finite sums. These are really cool. So how long is my video? 3 seconds, okay. If you have the sum of two different formulas, you don't have to do them as one big problem. You can break them up into two smaller problems. If you have a subtraction of two different formulas, you can break them up, find the sum of each one separately, and then subtract the two answers. If you have a constant times your formula, that constant can come out of the sum. If you're adding up just a constant, just a number, whether that's the sum of 2 or sum of 3 or sum of 5, whatever this is, it's just going to be however many you're adding up times the number. Because it's like, for example, if I had the sum of 3, this just means 3 plus 3 plus 3 plus 3 from maybe k equals 1 to 5. So one more. So 3 plus 3 plus 3 plus 3 plus 3, that's just the same as doing 3 times the 5. Or 15. Okay, so those rules are really useful, and I want to show you how to use them down here. So here we have two different terms. So what we can do is we can tackle this by breaking it up and doing the sum of the first term minus the sum of the second term. Further, we have a 3. That 3 I can actually take out of there and put in front because it's a constant multiple. So let's put the 3 in front of the sum. So the k stayed inside, but the 3 went out front. Now our sum is from 1 to n, and that stays the same for each of our summations. Now why did we need this? Well, if we look in the box over here, we have formulas. The sum of k squared, and the sum of k cubed. If it's just that, which if you notice here, we have just the sum of k and just the sum of k squared. We can use these formulas to find the answer. So this tells us what the answer is. This is a very cool formula. And if you go on in mathematics, you actually get to prove these formulas, which is a lot of fun. But then again, y'all already think I'm crazy, so maybe you disagree. All right, now notice it has to start the sum at 1 and go to n, and then we know what the formula value is. So the sum of all the k's is n times n plus 1 divided by 2. So keep our 3, and then the summation becomes n times n plus 1 all over 2. Minus the sum of the k squareds. Well, that formula is right here. That's n times n plus 1 times 2n plus 1 all over 6. You can work this out and simplify it, but I'm not worried about that. This would be fine. You do need to memorize these. You are going to need these formulas. Okay, I will show you a trick. If you look at the sum of k and the sum of k cubed, they're the same formula. K cubed just squares the answer. That's the only difference between the two formulas. All right, I am not leaving myself enough room here. There. All right, this guy here, all I could show you in this one is that this negative sign is actually a constant multiple, so he can actually come out in front. So we can make a positive inside and the negative go outside. So we just add up the AKs. That's all we can do there. All right, because we don't know what AK is. This one here, we have again two terms. So we break the sum up and we do the sum of the k plus the sum of the 4's. K goes from 1 to 3. K goes from 1 to 3. The first one here is actually one of our formulas, but this time we know what n is, so we can actually plug it in. So first I'm going to copy the formula. So the sum of the k's is n times n plus 1 all over 2. And we're going to go back and we're going to plug in our n value. So our n value is 3. plus the sum of the 4's. So this is actually this case here, the constant value rule. We're adding up 4 3 times. So literally you would do 3, the n, times 4. I'm going to write it down for now. So it's n value times our constant of 4. The n value here is 3. It's up here. So this is our n. So plug everything in. So 3 times 4 over 2 plus 3 times 4. And we end up with, let's see, that'd be 12 over 2 or 6 plus 12, which is 18. So instead of having to write out 1 plus 2 plus 3 and 4 plus 4 plus 4, these formulas helped. You might be thinking that's ridiculous. And I agree. For 3 terms, it's a lot easier just to write out the 3 terms and add them up. However, we're not going to be doing 3 terms. We're going to be doing infinite sums eventually, and we're going to need these formulas to be able to find those infinite sums. So practice these formulas on the easy problems so that when you get to the more interesting problems, you can do it. All right, find the sum as k goes from 1 to n of 1 over n. All right, so what is this asking us to do? Well, if I plug in 1 for k, wait, there's no k here. So what would our first term be? Well, n is a fixed number. So this n is a fixed number. This is actually a constant. So this is actually the sum of a constant, which means our formula is going to be the constant times the n. So our constant is 1 over n times the n that we're adding up. So we're adding up n plus 1, n plus 1, not n plus 1. 1 over n, 1 over n, 1 over n. And we're going to do that n times. So this ends up being the formula. Let me write it out just in case it helps you. So k equals 1, this is going to be 1 over n. K equals 2, this is going to be 1 over n. K equals 3, 1 over n. And we're going to keep adding this up n times. There are n of these, which is why we do n times 1 over n. And if we simplify, the n's cancel out, and we end up with 1. That's your sum. That's also something we're going to see when we get to the much larger problems. All right. If you have any questions, as usual, email me and let me know.